So in several previous videos, we looked at programming 1702A EPROMs with a manual programmer, and I've had limited success with that. I continue to get, honestly, just me making mistakes in the programming, single bit errors here and there, and it's become really frustrating. And over the holidays, I decided I wanted to get more familiar with KiCad, and this project evolved about, well, let's create a 1702 programmer for the Altair 8800. Why not? It would have been something appropriate back in the era. And that led me to digging into KiCad, looking at some online courses, and getting much more familiarity with it. While I was exploring programming 1702s, I come across this article from Popular Electronics February 78, which, again, very appropriate to the era, and this gave me really some good hints and schematics for moving forward on this. So let's go ahead and take a look through the article first. So basically, you can create this EPROM programmer that uses switches, just like my current one does, which really wasn't what I was after. But as you move down through the schematic, and we'll look a little bit closer at these pieces, there's a schematic section here for the front panel interface with the switches, but it's also designed that you could use a microprocessor to drive it. So basically TTL inputs for the addresses, TTL inputs for the data, and so it could be under microprocessor control. And this is what actually caught my attention, and I went, wow, I could basically use this schematic as is, design an interface to interface it to the Altair 8800 bus, and write some software and turn this thing into an EPROM programmer. So this is rather hard to see on its side here. Actually, let's explore to something else. We'll come back and look at the PCB in a minute. Let me see if I can find a photo I want. So this photo right here. So I went through and pulled out the schematic sections, rotated them, and then used color coding to indicate where signals connected between the sections. And the first thing he did with the design of this programmer is he's got a 33.3 kilohertz clock coming off of a 555, and he uses a series of counters to basically produce the programming pulses. So the prog signal comes to the system, and I should know where that is. Where does that come in at? Voltage enable. The schematic's a little bit difficult to see. That's reset, power up reset. Earlier I knew where this was, and now I'm not seeing it, and that's confusing. 13 program, there's a trigger for this. And why am I not seeing it? Anyhow, there's a trigger that resets the counter chain. And the counter chain starts counting up, and it produces the various waveforms and things that the 1702 needs to be programmed, and it really gets driven through this programming output here, this TC output here, the voltage enable output here, and then this circuit here that basically provides VDD and VGG to the chip. So you send a reset pulse, these count up until they're completed, and the way it's got it configured, it produces the various signals that are needed. If we move over here towards the socket driver, the socket driver basically gets the address bus coming in, and it can present the address bus through, or it can invert it with this TC signal. So this is called true. What did he say C stood for? It's either true or inverted, and drives these set of drivers here that can either ground the pin, or the pin gets pulled up to plus 47 volts. And it's kind of the same thing over here on the data pin. You set the data you want to program, and it's pulled up by a series of 47 k ohm resistors, or they're held to ground. You've got the VDD and VGG generator we looked over here that produce a couple of other high voltages, and then the programming pulse that comes to the part itself to say, hey, program the address here with the data here, and there's some weirdness about things got to be inverted, those kind of things. It's an interesting circuit to go through. There's the power supply section, again directly from the schematic. that basically takes about a 50 volt AC input, rectifies it, filters it to about 75 volts. 73.8 volts is what they call for. There's an adjustable current limited power supply over here that produces the plus 47, and the plus 59, which is 12 volts above for VBB. Again, pretty straightforward. All of these transistors are still readily available. A couple of just standard Zener diodes. So as I took this piece of the schematic to use in my design, I didn't take the 5 volt regulator here. Instead, I'll use the Altair power supply and a regulator on the programming board. A couple of things to note is I've designed this. I've kept the capacitor, I've kept all the numbers of all the components and all the boards identical, or as close to identical as I could, to the schematic here. So D1 through D4 on the board literally are going to be silkscreen D1 to D4. There's a few places where I've added either a 100 or a 101 in front of a few components because there was duplication across the schematic sections here. But overall, I was able to translate this design pretty easily to KiCad, and we can take a peek at that. Let me open up KiCad here. I've got eSchema opened, and this first page here is just the driver circuit, basically to drive the programmer. There's a couple of latches here. One of them latches the data to be programmed. The other one latches the address to be programmed. These are just 8212s, so very period appropriate parts. There's some decoding logic here for the ports, and you can decode A15 to A11 to either be a 1 or a 0 with some jumpers. That gets decoded, and with A8, A9, and A10. And the inclusion here of in-strobe and out-strobe, that's what I was looking for. We decode 1 of 8 ports, of which only the top 4 are being used currently, and use in-strobe or out-strobe ultimately to latch those into these latches. There's 4 ports I'm using. There's the base port, whatever these are set to, which latches the data. That port plus 1 latches the address. Simply sending a write to this port plus 2, so this prog signal will go low when we do that write. That's enough to trigger the entire chain and get the timers or those counters to do their thing. And then there's a check ready, which is actually an import. And check ready is fed from this ready status here. And in my case, that ready signal comes back on data 0. So I can look doing an import at that base port plus 3 at this bit here to say, is the programmer busy or not? If I follow this correctly, it says it takes about a ½ second per byte to program. So really, this is just a circuit I designed to drive the thing. We can drive into the power supply section here, and this was just really schematic capture from what was in the article. So we've got, very similar thing to what we saw. We've got our diode bridge, our 50 volt AC input, a filtering cap, a fast blow fuse, and really it's just the same circuit all the way through. So very similar. Let me get back up out of here. The socket driver should look very similar to that schematic. Again, it's really the same thing. We've got that TC signal. We've got the row address, or the addresses to be, the address to be programmed, the data to be programmed, and it's just very similar. The 47 volt pull up to those pull up resistors, a way of feeding in the program ports and that VGG and VDD. So again, this is really identical to what was in that schematic in the original article. I'll hop up a level here again. And the clock chain, and this is scrolling the wrong way. This is again laid out very much like it was in the schematic. Component locations and stuff drawn here. It just made it easier to draw out. We've got our 555 generating that 33.3 kilohertz clock signal. There's the program signal, where the program signal comes in from. So when I do that write to base port plus 2, this gets pulsed low. It does a reset of these first 2 counters. The counter chain fires off, produces the various pulses. There's a programmer's active LED here, and I added a high voltage as active, and I'm actually thinking after I got this done that this LED is going to be on when the high voltage is off. I may have to invert that signal. We'll find out in the design. So again, everything here really similar, really identical to the original design. IC numbers match the original schematic. Like I said, there's a few components like C103 here and C104. This was C4 in that original schematic and C3. But C4 and C3 were also on other pages, so I just added, like I say, a 10 in front of some part numbers. But again, this really is C4 in that original schematic. So from all of this, I went through, and once I was happy with the schematic and validated as best I could, I had it captured correctly. I went ahead and fired up a printed circuit board. This is the board I came up with. So this is an S100 card, only it has 1.5 inches of extra height here. And that brings the programming socket and the large capacitor here above the height of the other boards. Gives me some room, and this way you have access to the programming socket without pulling the board out. I will be feeding this board with the same 50-volt AC in the schematic. We've got that diode bridge, filter cap, and really the socket driver really is this section here. We've got those XOR gates. We've got the address and data coming in. We've got the driver transistors we saw to the socket. The couple of other signals that come in. The programming LED. So really this is the socket driver in this corner. The driver chain for the timing is kind of scattered across the board here. Probably could have done this better. The 555, the various clock drivers. Through here, I guess it's not that bad really. Down here, the two latches live up here. The jumpers for the port you want the board to be on. The decoding logic lives in here to decode the ports. And really that's what I came up with. It's interesting it's positioned funny. Like, oh, it's just me having the page not centered on the screen. This was done with a combination of manual routing and auto routing. Really both, so I kind of went both ways. You know, these major power signals like the +8 and the ground were hand routed. The interconnect through the 7805 here, it's hard to see here, was hand routed. I think this was hand routed up here. There were places that I hand routed for the larger current traces, and then let the auto router actually route the rest of this. I could have spent some time and actually probably mapped what pins on these 367 buffers were used for A0, A1, etc., and got a little cleaner auto routing down here. I didn't take the time to remap those. I just went with them directly as I drawn them in the schematic. Board is what it is. I've had 5 of them manufactured by PCBWay. It was about $100 with delivery. And really the next step in this project is to begin to assemble this. I'm going to kind of do it in stages. Right now I have all the resistors stuffed onto the board. I need to solder almost all the resistors. I've already run into a couple of minor issues here. Don't affect the schematic. They were mislabels, like this 820 ohm resistor was labeled 8.2 k ohm. He's really 820 ohm. But a couple of minor nits like that I've hit. But again, you know, this 4.7 k ohm resistor here is actually R1 in that section of the schematic, and I've added the 10 because there's an R1 elsewhere. All the resistor numbering here has been kept identical to the schematics. Like I say, I've tried to keep this as absolutely close to those original schematics as possible. I'm not happy particularly with the footprints I picked for the transistors. I could have went with one where there was a gap between the emitter base and collector pins. I've got enough room here. Those could have been wider. This is just going to be really tight to solder on the back. I may change that, but again, that affects the layout. Pretty happy with the boards I got back. We can jump back here. Why can't I move through the photos? Really? You're going to be stubborn? Well, that's obviously not what I wanted. Let's get back and find the 2 photos. Here's the front of the board. So there's a scan of the board as it came back from PCBWay. I'm pretty happy with this overall. I think it turned out pretty well. This is only the second board I've ever designed in KiCad that I had manufactured. So there was a whole lot of learning that went on here to understand how to do this. A whole lot of learning. I had fumbled with KiCad in the past many times and never really got to something I liked and I felt like it was completed. This will eventually be released as open hardware, not that there's more than probably me in the world who care about a 1702 EPROM programmer for an Altair 8800. This would work in the MSI 8080 as well. It's not designed for the IEEE 696 bus. It's designed for the original Altair S100 bus. So really there's the front of the board. I've spent a lot of time, as you can see, getting all the part numbers and everything kind of in place so it makes some sense. It's a little crowded up here. And now photos is going to work again. Back of the board. You can see a little heavier traces here on things that handle power. Still struggling with KiCad to get good fills. Debating in my head some ways to actually get better copper fills. Got to do some more research. Anyhow, I think this kind of really wraps up this intro video. I don't know that I have a whole lot more to say about it. We can go in here while we're playing. Take a look at the board in the 3D viewer. It didn't turn out bad. This capacitor is a monster. It's about 2 inches long. The cap I used went partly because it was axial rather than standing up off the board. I like the looks of it. It's kind of more period appropriate for a cap of that size. I ended up with 0.4 spacing on the resistors, and so my 1/4 watt resistors just barely fit. The leads are bent right at the body. I should have gone with a little bit larger footprint there. I already mentioned I don't like the footprints I used on the transistors, particularly if I always fight with this to get it to do what I want. As the spacing's pretty tight here. I mean, it's very manageable. It's just tighter than I wanted. Didn't have to be that tight. But pretty happy with this. I'm sure I've made 100 stupid design layout things because I didn't really know what I'm doing, and I'm not a printed circuit board designer. The last time I did printed circuit boards, we were hand taping on clear plastic, double-sided, and then using a photography to reduce it down to the full size. Bright light exposure and etching. So very much hand done. I struggled to get a good footprint here for the fuse. I ended up using a large resistor footprint because the fuse I've got is a glass fuse with wire leads on the end. Looked at some nice socketable fuses and they were very spendy. I just went, just a glass fuse with wire leads will be good enough. Don't know what else I can say. I did drop in some test points here to get points where you can actually measure voltages, just because that's useful. There's a ground one up here that's probably shouldn't have been put there. It probably should have been put over here, but I dropped a ground one in there like a dummy. There's a couple other test points floating around here. Just one for the +5, the +47, the various voltages. This board does expose that 75 volt DC on traces on both the back side and the front side, so reaching in with it powered up to change a part could be quite fun. I considered putting a relay on here I could control to actually energize the high voltage or not. I didn't do that in this design. That may happen in a future design if I actually have success getting this thing to run. Anyhow, I will wrap this up here. I've rambled on long enough. And I'll see you in future videos as we assemble and test the board.